Welcome back, everybody. So this is a video going over section 7.3. We should definitely be able to get through all the notes today on section 7.3. Just so you guys know where we're headed, today we're doing section 7.3. Tomorrow I will give you the review sheet for chapter 7. And then obviously no school Friday. On Monday we will review, and then I can actually do stuff next Tuesday, Wednesday. A lot of the other classes can't because it's late starts, right? But lunch periods don't get late starts, so we have a full class period on Tuesday and Wednesday of next week. So we will be doing our chapter 7 assessment on Tuesday of next week. I believe it's Tuesday. It's either Tuesday or Wednesday. And then the day after that, we'll be doing our chapter 7 project. Quite simple, though. Chapter 7 project's pretty easy. And it actually has a lot to do, it's a good segue, it actually has a lot to do with what we're talking about today. Because just like what we talked about with critical, or what was that, error margins for population mean, right? We talked about error margins for population mean. That was the chapter 6 project that you guys worked on. We were, what was that called? Error margin, and then the high and the low. Why can't I think of that? Interval, confidence intervals. There we go. Couldn't think of the words. Confidence intervals. We did confidence intervals for your means of your project. Just like we had that, we're going to be doing hypothesis testing for your project, right? Did you know sigma in your projects? No, you didn't know sigma. You didn't know the population standard deviation, but what you did know was your sample standard deviation, right? And that's what we can use, right? That's what we can use. Guidelines for finding critical values in a t-distribution. Just like we had with confidence intervals, we had to switch from using a z-table to a t-table. Same exact thing, right? Same exact thing. First thing is identify the level of significance, alpha. Second thing, identify the degrees of freedom. Obviously, it's always going to be n-1, just like you had with the t-tables from before. Find the critical value using table 5. They call table 5 the t-table. Table 5. If the hypothesis is left-tailed, you use one tail. If the hypothesis is right-tailed, you use one tail with a positive sign. If it's two-tailed, you use two-tailed. If you look at the t-tables, I'm just going to pull out the yellow packet here. If you look at the table 5, the t-distribution, you see up at the very top, we kind of ignored the very top of the table before, but you see one tail, two tail, right? You see one tail and two tail. One tail alpha, two tail alpha. Now we just have to pay attention to whether it's one tail alpha, two tail alpha. If it's one tail alpha, well, that's either a right tail or left tail, right? Now, if it's a left tail, just use these straight up numbers. If it's a right tail, you use the opposite of these numbers, right? Because, I'm sorry, I said that the opposite way. If it's a left tail, you want the negative score. If it's a right tail, you want the positive score, right? Because it's going to be equivalent on either side, right? These bell curves are always symmetrical. So therefore, if you wanted the left tail, use the negative version of that t-score. If you want the right tail, use the positive version of that t-score, And then if you want a two-tail, well, you just got to use the two-tailed topper, two-tailed chart. Because honestly, if you think about alpha, if I change from one tail to two tail, what's that doing to alpha? If I change from one tail to two tail, what's that doing to alpha? It's halving it, right? So that's why you see if it's a one tail of, if it's a two tail 0.2, one tail would be 0.1, two tail 0.1, and a 0.05. So it's got that 1 to 2 relationship in there. And honestly, the rest of the hypothesis testing remains exactly the same. Everything that we learned about hypothesis testing is exactly the same. That's weird. Is exactly the same as it was. Okay. So let's just start exactly as we started before. Oh, actually, people are still copying that. I'll pause for a moment. I think we got a good joke for you guys. So this piece of rope walked into a bar. Did I say this one already?
No.
Just go with it. This piece of rope walked into a bar. This length of rope. Right? The bartender says, "Whoa, whoa, whoa! We also have rope here. Get out." So the piece of rope walks outside, beats himself all up, gets himself all frayed, ties himself in a big old knot. Then he puts on those like glasses with like the nose and the mustache. Walks back in, and the bartender says, "Hey, aren't you that length of rope that just walked in here?" And he goes, "No, I'm afraid not." Get it? I'm afraid not.
Yes, that was very good.
Afraid.
Oh, Mr. Walker, let's see if you get this one.
That was pretty
A guy, a Roman, walks into a bar.
Yeah.
And says, "Can I get an extra large beer?"
Yeah.
And the bartender goes, "All right," and gives him 40 beers.
XL, because X is 10, L is 50, so XL would be 40.
I got one.
Yeah.
A cheese salesman assaults me. How dare he?
How dare he?
How dare he?
How dare he? Two pretzels walked down the street.
One was assaulted.
One was assaulted.
That's Mr. Keller's
I
coach.
know. I was gonna cite my source, Keller, 2023. Parenthetical reference there.
I like
All right, here we go.
That's the best.
That goes good.
Find the following critical values. So let's go left-tailed test with an alpha 0.05 and n is 13. You know what? Let me pull up the chapter 7. No, that's not it. Where is my T table? There? No. Where's my T table? Chapter 5? Nope, that's my standard normal table. Chapter 6? There it is, T distribution table. Come on.
Try it 3 times.
There it goes. All right, so here's my T distribution table, right? So this is what I'm talking about up at the top, one tail, two tail. We were working with levels of confidence before, but now we're not working with levels of confidence. We're talking about alphas. All right, so if I go back to my notes here, and I want left-tailed tests with an alpha 0.05 and an n of 13. All right, so how many degrees of freedom do I have? What's my degrees of freedom? 12. So I'm going to look at at row 12, degrees of freedom, alpha 0.05 for a one-tailed test. Okay, where was it? Right here. Alpha 0.05 for a one-tailed test, right here. So this is the column that I'm going to be looking at, and the row that I'm looking at is the 12. 1.782. 1.782. 1.782. However, if this is a left-tailed test, what do I have to do with it? Make it negative. There it is. Okay. All right, right-tailed test, alpha 0.01 with an n equals 7. All right, right-tailed test, alpha 0.01. Okay, one tail, alpha 0.01. And the n was 7, so therefore degree of freedom, 6. So 3.143. 3.143. 3.143. Now, do I need to make a negative? No. We're good. 3.143. Two-tailed test with an alpha 0.1 and an n equals 16. All right, so that means two-tailed of 0.1. Two-tail, 0.1, and my n was 16, so I go to row 15. 1.753. 1.753. 1.753. Now, the interesting thing here is that I have to think about it both plus and minus, right? Both plus and minus. Questions about that? Why do I have to think about it both plus and minus? Because it could be above or below, right? I could reject if it's really high or really low. Because if my claim is that something is equal, it just has to be not equal for the alternate to be true. All right, so our test statistic is the t-score, right? The t-score. And there is our formula. It's basically using a new formula here. Not really new, we've used it before. X bar minus mu divided by S over square root of n. The t-test for a mean is a statistical test for a population mean. The t-test can be used when the sample is random or the population is normal, or n is at least 30. And again, we use our degrees of freedom as n minus 1. Now, be careful here. You know what the very common mistake is to do? Accidentally put an n minus 1 into the formula. No, I'm not using an n minus 1 in the formula. I am using an n in the formula. I use the n minus 1 when I talk about my degrees of freedom. Okay, that's the only time I'm going to be using my n minus 1 for these, is when I'm talking about my degrees of freedom. The n goes in, it's just straight up n, straight up your sample size for your t-score. X bar minus mu over s divided by square root of n. Okay, and again, x bar is our sample mean, s is our sample standard deviation, right? I don't know sigma, so it's just s. Okay. Now, the rest of this, right? This next slide that I have is exactly the same as what we had done yesterday for z-score, but now we're just going to talk about it with t-scores. Yeah. Let me go here.
Can you go back one?
Oh, sorry.
I just need to finish copying.
You're all right.
There you go.
Why'd the cookie go to the doctor?
Why?
No problem.
No.
Did you hear about the cannibal who showed up late to the potluck? He got the cold shoulder. That was a quality joke. You guys,
No, it was quality. I don't
the
really.
cold shoulder, get it? The cold shoulder? Cannibal? You know what a cannibal is?
Yeah,
Guy who eats other people.
Oh, I forgot the. I
Should have late to the potluck. You
That's why I
got the
didn't
cold
use it.
shoulder. Like the shoulder was cold. Like there was shoulder on the menu.
I think
And he wanted to eat it, but it was cold because it showed up late. But he also, you can interpret it as like cold shoulders, being like, you know, what are you here for?
Oh, you were late.
All right.
Get it, Brandon? Okay, I think the explanation is.
Calm down. All right. So guidelines for using the t-test for a mean. So this is all exactly the same as z-test, right? Same thing. State the claim in math words. Identify null and alternative hypotheses. State the level of significance. Identify degrees of freedom and sketch the sampling. We don't really need to sketch, honestly. Determine any critical values. Determine any rejection regions. We talked about two different ways to decide whether to reject or not reject. We talked about using p-values and then using rejection regions. I got to be honest, I like using rejection regions a little bit more. If I had a choice, I'd probably be using rejection regions rather than p-values. I don't know. It's the same work. I don't know why. Just do it that way. So that's the way that I'm going to be doing the hypothesis testing. If it doesn't tell me to use p-values, I'm going to be using rejection regions. Make a decision to reject or fail to reject null. Find your t-score first. Then make a decision whether to reject or fail to reject your null. And then write that final statement in the end, whether you interpret or how you interpret your decision based on the context. Let's do it. I want to do two of these. Okay. Your friend states that his make of TV usually sells for at least $2,500. You don't believe him because you think he's just exaggerating about the deal he got. You randomly sampled 10 of the television owners, and the mean price was $2,400, with a standard deviation of $150. Assuming the prices are normally distributed, do you have enough evidence to reject your friend's claim at the 0.05 or 0.01 low? All right. So what's the claim? What's the claim? What's your friend saying?
U equals 2,500.
Is
Greater than. Oh.
Greater than or equal to, right?
I see it. That's an expensive TV.
Right. Mu is greater than or equal to 2,500. And it's important that we state the claim is greater than or equal to. Why? Because now where is the claim going to go? In the null, right? Because my angle is that I would love to do what to his claim? Disprove. I am trying to disprove his claim. So I'm going to put his claim in the null. And then if I can choose to reject the null, then I can truly disprove his claim. Therefore, the alternative is mu is less than $2,500. All right, we randomly sampled 10 of the television owners. All right, so that means n is 10. Out of those 10, we had a mean price of $2,400 with a sample standard deviation of $150. So this is S, not sigma. Assuming the prices are normally distributed, and we have to have that assumption because we only chose 10 people. Assuming the prices are normally distributed, do you have enough evidence to reject your friend's claim? Let's start with the alpha 0.05 level. Now, if I think about it this way, could I reject at the 0.05 level and then fail to reject at the 0.01 level? Yes, right? If I fail to reject at the 0.05 level, could I possibly reject at the 0.01 level? No. If I fail at the 0.05, I'm going to fail at the 0.01, right? If I reject at the 0.05 level, that automatically doesn't mean that I have to reject at the 0.01 level, because the 0.01 level is stronger, right? You can think about it this way. Think about it as confidence, right? 95% confidence versus 99% confidence, right? That might, because I know some of you guys sometimes might struggle with the, what's a stronger statement. Think about it as a percentage. This is like a 95% strength statement. This is a 99% strength statement, right? So this is a stronger statement than 0.05. All right. Now, that being said, what do you want to do first? You want to find the t-score or the rejection region? Let's do the rejection region first. Yeah, because these are kind of going to be independent of one another. So if I'm talking about the alpha 0.05 level, let's go with the alpha 0.05 level. How many degrees of freedom do we have?
It's 9.
9. Good. Degrees of freedom is 9. All right, so therefore, what is my rejection region? Okay, let's go back. Now, is this a one-tail or two-tail test? One tail, right? And this is a left tail, right? So this is a left tail alpha 0.05. So alpha 0.05, degrees of freedom 9, one tail 0.05, degrees of freedom 9, 1.833. 1.833. So I've got 1.833, but this is a left-tailed, so what do I have to do to that? Make it negative, right? Now, when am I going to choose to reject the null? When it is less than or greater than? 1 point less than. So if t comes out to be less than negative 1.833, basically this, and maybe it is a good idea to sketch. There is your critical value, right? Your TC. If my true t-score turns out to be in that region, then I can reject the null. If it's not, then I can't, right? Let's do this right away. Let's find the alpha 0.01 level. If it's the alpha 0.01 level, my degrees of freedom is still 9. Let's find the rejection region now. Now, what's going to happen to my t-score before I even look at it? Decrease, really, right? Right, the value is going to go up. I see what you're saying. But it's going to decrease, right? So now let's say alpha 0.01. Same degrees of freedom as 9, right? But now 0.01, 2 columns over. 2.821. 2.821. And again, we got to take a negative. Negative 2.821. So now this critical value is now over here, right? So it's a harder target to hit, right? Okay, so let's see if our t-score falls in either of those rejection regions. And again, the t-score is going to be x bar minus mu, so 2400 minus 2500 divided by s divided by the square root of 10. Square root of n. Not n minus 1, Not 9. 10. All right. So we have negative 100 divided by, because that's 2400 minus 2500, divided by 150 divided by square root of n. Square root of 10. Not square root of 0, square root of 10. All right. Negative 2.11. Okay. What's our choice? What's our decision at the 0.05 level? Do we reject or fail to reject? We reject. Good. Yeah. So at alpha equals 0.05, we say, well, that's negative 2.11 is less than negative 1.833. So our decision is that we reject the null. Okay, well, at the alpha 0.01 level, negative 2.11 is not less than negative 2.821. We fail. Okay. So let's make a statement in context. So our statement in context basically says we can disprove the claim at the 0.05, that's a 0.05 level of significance. But we don't have enough information, have enough info to reject or to disprove the claim at the 0.01 level. Does that make sense? We can disprove the claim at the 0.05 level of significance, but we don't have enough information to disprove the claim at the 0.01 level of significance. Questions about that? Can we do one more? Yeah? Why not? And let's do just this. You know what? Let me boop, boop, boop. Okay, your math book states that the average height of 18-year-old females is 64 inches. You don't think that sounds right. You randomly sample 40 18-year-olds, and you get a sample mean of 64.5 inches with a standard deviation of 1.4 inches. Do you have enough evidence to reject the book's claim at the alpha 0.1 level? Okay, so what is the claim? What is the claim?
Equals 64.
Yeah, the claim is that mu is 64, right? That's what the book is claiming. What would I love to do about the book's claim? Reject it, dispute it, disprove it, right? So that's good that I can put the claim in the null. We're just a bunch of negative Nancy's today, trying to disprove everybody. So mu is not 64 is the alternative. Okay, so let's define what we know. We have mu 64. You don't think that's on the random. 40. N is 40. X bar is 64.5. S is 1.4. And we have the book's claim at the alpha 0.1 level. Okay, so now let's find our rejection region. Alpha 0.1, degrees of freedom 39. Now, is this a one-tail or two-tail test? Two-tail test, because it's an equality. So now let's go into our table with a two-tail, 0.1, degrees of freedom 39. So second column, right? Yeah. Two-tail, 0.1. Second column, we got 39, 1.685. 1.685. So, yeah, we want to say, so our rejection region, right? Our rejection region is going to be, now, it could either be smaller than negative 1.645 or greater than positive 1.645, right? So we can say if z, nope, not z, t. If t turns out to be less than negative 1.645 or t is greater than 1.645. Because again, think about your bell curve. Here's your critical values here. I want to be able to hit that shaded region, right? So if my actual t-score falls in that shaded region, then I can reject the null. So it's got to be either less than 1.645. Oh, I have 1.685. I better check on that real quick. It was 8.5. Poop.
Hey, at least you caught it.
Yeah, that's true. There we go. Just turn those 4 into 8s. All right, let's find our actual t-score. So our actual t-score, x bar, 64.5, minus mu, 64, over s, 1.4, divided by the square root of 40. So 64.5 minus 64 is 0.5. So now, right away, because our difference from our mean to x bar is positive, the only chance of me rejecting my null is going to happen in the positive side of this thing rather than the negative side of this thing, right? Because this is a positive number, that's the only chance I've got. Let's see if it comes to pass. Divided by 1.4 divided by the square root of 40. Let's see where we're at. 2.26. Do we have a winner? Yeah, we do.
Woot, woot.
Yeah. So we can say because 2.26 is greater than 1.685, we can choose to reject the null. We can choose to reject the null. So let's make our statement in the end. We can disprove the claim. And if you want to get wordy, you can actually state the claim that the math books claim that the average female height is 64 inches tall. We can disprove the claim at the alpha 0.1 level of significance. Make sense? You know, the difficult part about chapter 7 will become, not only identifying what to do, but also, what does the context of the problem tell you to do? Do I have sigma? Do I not have sigma? Do I use z-score? Do I use t-score? Do I want to disprove? Do I want to prove? Where does the claim go? There's a lot that goes into it. Yeah. All right, here is the homework for section 7.3. I think this is fun stuff. I love this stuff. Love it. So glad Mr. Delap didn't teach it to me.
Is that sarcasm?